Hello everyone and welcome back to our course on SerDes Basics. In this video, we're going to focus on the fundamental behavior of signals and timing in high-speed systems. In the previous video, we looked at the overall structure of a SerDes link and followed the path of data from the transmitter through the channel and into the receiver. We saw how the transmitter converts parallel data into a high-speed serial stream, how the channel distorts that signal as it propagates, and how the receiver works to recover both the data and the timing from that imperfect waveform. At low speeds, we often think of digital signals as perfect square waves. They have clean transitions between 0 and 1. But in high-speed SerDes systems, those waveforms can look anything but clean. Even at the transmitter, the signal is not perfectly square, and once it passes through the channel, it becomes further degraded. So instead of thinking in terms of perfect waves, it's more accurate to think of a signal as a time-varying voltage waveform that represents data. They have finite rise times, limited amplitude, and are affected by noise and distortion. That means the receiver isn't simply reading ones and zeros. It is sampling an analog waveform and deciding what those values represent. If the signal is a waveform, then the next question is, when should the receiver sample it? If the receiver samples at the wrong time, it may capture the signal while it is transitioning between 0 and 1, leading to an incorrect decision. To understand this, we introduce the concept of the unit interval, or UI. The unit interval is simply the time duration of one bit. At high data rates, the UI becomes very small. For example, at 10 gigabits per second, one UI is only 100 picoseconds. That means the receiver has a very tight window in which it must sample the signal correctly. Ideally, the receiver samples at the center of each bit period where the signal is most stable, but this requires precise knowledge of timing. Let's start with how timing is created. At the transmitter, timing is generated using a phase lock loop, or PLL. The PLL takes a low frequency reference clock and generates a very high frequency clock that determines the data rate of the link. This clock drives the serializer and ensures that bits are launched onto the channel at precise intervals. In other words, the transmitter defines the timing of the data stream. However, no clock is perfect. Real PLLs introduce jitter, which is small variations in the timing of edges. From a system perspective, the PLL acts as a jitter filter. It tracks low frequency variations from the reference. It filters high frequency noise, but it can also introduce its own VCO phase noise. We'll discuss jitter more in the next video. So the PLL directly impacts how much timing uncertainty is present in the transmitted signal. But there's a key challenge. The receiver does not receive this clock directly. The transmitter defines timing, but the receiver has to reconstruct that timing from the signal itself. So how does the receiver know when to sample the signal? This is where a CDR comes into play. Instead of relying on a separate clock signal, the receiver extracts timing information from the data itself. The idea is that transitions in the data from 0 to 1 and 1 to 0 contain information about timing. The CDR circuit observes these transitions and adjusts its internal clock so that it aligns with the incoming data stream. CDR performance depends on data transitions. For example, long strings of identical bits means no timing updates. This is why many systems use encoding schemes like 8-bit, 10-bit to guarantee sufficient transitions. Over time, the receiver locks onto the data and maintains synchronization. But this process is dynamic. If the incoming signal changes due to jitter or noise, the CDR must continuously adjust its timing to stay aligned. This is one of the most important and complex functions in a SerDes receiver. Once the receiver has recovered the clock, it uses that timing to sample the signal. At each sampling point, the receiver measures the voltage of the waveform and decides whether it represents a logical 1 or 0. This decision is made by a comparator or slicer, which compares the signal to a threshold. If the signal is above the threshold, it is interpreted as a 1. If it is below, it is interpreted as a 0. If the timing is correct and the signal is sufficiently clean, this process works reliably. But if the timing is off, or if the signal is too distorted, errors can occur. To better understand why timing is so critical, it helps to think about something called the sampling window. When the receiver samples the signal, it is trying to make that decision at a point in time where the waveform is most stable and farthest away from uncertainty. Ideally, that point is at the center of the unit interval, where the voltage difference between a logical 1 and 0 is the largest. I'm going to use images of eye diagrams to explain what the timing window is. An eye diagram is created by overlapping multiple unit intervals on top of each other. Eye diagrams and other channel metrics will be covered in a later video. In reality, both the signal and the timing are imperfect. The signal is distorted by the channel, and the timing is affected by jitter. As a result, the safe region where correct decisions can be made begins to shrink. This region is often referred to as the timing margin. If jitter shifts the sampling instant too far, or if the signal transitions become too slow, the receiver may sample closer to the edge of the bit period where the waveform is less defined. This dramatically increases the probability of making the wrong decision. At high speeds, communication is no longer about just sending voltage levels. It's about ensuring that both timing and voltage stay within a safe margin where correct decisions can be made. So far, we've discussed signals as if they were single-ended, meaning a single waveform. But in almost all high-speed SerDes systems, signals are transmitted using differential signaling. Instead of sending one signal, we send two, a positive signal and a negative signal. These two signals are equal in magnitude but opposite in polarity. The receiver does not look at either signal individually. Instead, it looks at the difference between the two. If the positive signal is higher than the negative, the receiver interprets a 1. If the negative is higher, it interprets a 0. This approach has several major advantages. First, it improves noise immunity. Any noise that affects both lines equally, also called common mode noise, gets canceled out when the receiver takes the difference. Second, it reduces electromagnetic interference, or EMI, because the currents in the two lines flow in opposite directions, minimizing radiated emissions. And third, it allows for more reliable detection at high speeds, especially when signal amplitudes are small. Differential signaling is one of the key reasons why modern SerDes systems can operate at such high data rates. Now let's bring these ideas together. A SerDes signal is not always a clean digital waveform. It is an analog signal that evolves over time and is affected by the channel. The transmitter uses a PLL to generate precise timing to launch data onto the channel. The receiver uses a CDR to recover that timing from the incoming signal. Once timing is recovered, the receiver samples the signal at the correct instant and determines the data values. And all of this occurs using differential signaling to improve robustness and noise immunity. In this video, we focused on the fundamentals of how signals behave and how timing is established in a SerDes system. We introduced the idea that signals are analog, not ideal, and that precise timing is critical to correctly interpreting data. We also saw how clock generation and clock recovery work together to ensure that the transmitter and receiver stay synchronized, even without a shared clock. And we introduced differential signaling as a key technique for maintaining signal integrity at high speeds. Now that we understand how signals behave and how timing works, we're ready to look at what happens when things go wrong. In the next video, we're going to examine the imperfections of real-world channels in more detail, including loss, jitter, noise, and intersymbol interference.